we are going to see about black body radiation and the quantum hypothesis. Radiation is a wave which consists of oscillating electric and magnetic field. The electromagnetic waves are perpendicular to each other and they are perpendicular to the direction of its propagation also. It was characterized by its wavelength and frequency. Frequency is nothing but number of oscillations per second, which are related as c is equal to h nu. C is velocity of the wavelength, h is Planck's constant, and the value of velocity of wavelength is also equals to the velocity of light, that is 3 into 10 power 8 meter per second. The emitted radiations by any solid at particular temperature is a result of its vibration, and the low temperature produces emitted radiation at low frequency with large wavelength, that is infrared radiations. When the temperature increases, not only the amount of radiation increases but also more radiations of smaller frequencies are emitted from that solid. At any temperature, the radiation of a solid has continuous range of frequency to the gases which produce line spectra contrast to the light. Different solid emit radiation at different rates at the same temperature. If we are giving the same temperature for different solids, means it will emit different radiations at different rate. The rate is maximum when the solid is perfectly black, and it can absorb all radiations that falls on it. Consider this hollow sphere. In this a hollow enclosure having a small hole is considered. A small hole is nearest approach to a black body because the radiation entering through this chamber, the hole is absorbed completely due to the repeated reflections inside the enclosure. The intensity of radiation, that is the total radiation emitted per unit surface area from a black body, depends only on the temperature, and it is independent of the nature of the solid. So the energy distribution of black body radiation could not be explained by the application of classical physics. The correct expression was derived by Planck on the basis of quantum theory of radiation. According to this theory, radiant energy is emitted or absorbed discontinuously in the form of tiny bundles of energy, that is known as quanta. So each quantum is associated with a definite amount of energy E, where E is energy in joules, nu is the frequency of radiation in reciprocal seconds, and h is the fundamental constant known as Planck's constant. The numerical value of Planck's constant is 6.626 into 10 power minus 34 joule second. So the value of quantum of energy is also given by h nu, that is hc nu bar, where nu bar is the wave number defined as the reciprocal of wavelength. That nu bar is equal to 1 by lambda. Evidently, nu is equal to c by lambda, which can be rewritten as c nu bar, and E is equal to hc nu bar. So a body can emit or absorb energy only in whole number multiples of the above set quantum, 1 h nu, 2 h nu, 3 h nu, and so on up to n h nu. Energy in fractions of quantum cannot be lost or absorbed. This is known as quantization of energy. So based on this theory, Planck obtained the following expression for energy density of black body radiation. E of nu d nu equal to 8 pi h nu cube divided by c cube into d nu by exponential of h nu by kt minus 1. So the above equation adequately accounts for the black body radiation curve at all wavelengths obtained at different temperature, which was represented here. So the Planck was awarded Nobel Prize in 1980 for propounding the quantum theory of radiation. Then we are going to see about photoelectric effect. J.J. Thomson, he is a famous scientist. He observed that when light of a certain frequency strikes the surface of metals, electrons are ejected from that metals. This phenomenon are known as photoelectric effect. A few metals show this effect under the action of visible light, but many more show it under the action of energetic ultraviolet light. So cesium, which amongst the alkali metals has lower ionization energy, and the metal from which electrons are ejected most easily by light, this metal is therefore used largely in photoelectric cells. So after making careful studies of photoelectric effect under different conditions, the following observations were made. For each metal, a certain minimum frequency of incident light is needed to eject an electron. So this is known as threshold frequency, which was represented as nu naught. A light of smaller frequency than this cannot eject electrons no matter how long it falls on the metal surface or how high is its intensity. So the threshold frequency is different for different metals. So the kinetic energy of ejected electrons is independent of the intensity of incident light but varies linearly with its frequency. So the number of ejected electrons from the metal surface depends upon the intensity of incident radiation. The greater the intensity, the larger the number of ejected electrons. So the photoelectric effect cannot be explained on the basis of classical wave theory of light. According to this theory, energy of light depends on its intensity. So light of any frequency, if made sufficiently intense, can cause ejection of electrons, but this does not happen. So the quantum theory of radiation affords an easy explanation for photoelectric effect. According to this theory, the light consists of bundles of energy which is called as photons, the energy of each photon being equal to h nu, where nu is frequency of light. So when photon of light of frequency nu naught, that is threshold frequency, strikes an electron in a metal, it impacts its entire energy to the electron. This energy enables the electron to break away from the metal atom and overcoming the attractive influence of the nucleus in that particular metal. So each photon can eject one electron. If frequency of the light is less than nu naught, there will be no ejection of electron. So suppose the frequency of the light falling on a metal surface is higher than the threshold frequency. Let it be nu. When photon of this light strikes a metal surface, some of its energy, which is equal to the energy binding the electron with the nucleus, is consumed to separate the electron from the metal, and the remaining energy will be imparted to the ejected electron to give it certain velocity, which is known as u, that is initial velocity. Then the kinetic energy will be equal to half mu squared. So Einstein applying this quantum theory and showed that h nu is equal to phi plus half mu squared, where phi is the threshold energy or work function of the metal and half mu squared is the kinetic energy imparted by the ejected electron, and evidently phi is equal to h nu naught, and substituting equation 2 in equation 1, we will have h nu is equal to h nu naught plus half mu squared, and then half mu squared is equal to h of nu minus nu naught, that is we are taking h as the common factor. This equation is known as Einstein photoelectric equation, and this equation was tested by Robert Mulliken, and the kinetic energies of emitted electrons for various frequency of light were determined by finding the opposing potential to stop the photoelectric current and knowing kinetic energy corresponding to a given incident light of frequency nu and knowing nu naught, that is the threshold frequency required just to cause ejection of electron, and the value of h was calculated. It was found to be 6.570 into 10 power minus 34 joule second. This is an excellent agreement with the value, that is 6.626 into 10 power minus 34 joule second obtained from the experiments on black body radiation. So it is evident from the above discussion, the photoelectric effect can be explained only on the basis of corpuscular or particle theory of light, but certain phenomena such as diffraction, interference and polarization of light can be explained only on the basis of classical wave theory of light. Thus light is considered to have a dual character. It behaves as a particle and so as wave. Thank you.